tonight.
Sorry?
I'm really out of it tonight. Apologies if I don't pay any attention.
You have to pay attention. So, I think it's time to start. Okay, so today we start chapter 5. It's called the Unruh effect, and this is the program. And I'm sure you have heard about this effect before. So, no?
No, I mean, like, I have met this person. So.
You have what?
Met Bill Unruh.
But did he explain to you?
No.
So, you know, it is my impression, and I think many people's impression that you know, that even among students which are very familiar with the standard formulation of quantum field theory in Minkowski spacetime, for them it's really difficult to abandon this intuitive picture of particles as something which is, which is real and objective and unambiguous. And even after going over the path of the last chapters, you realize that in core spacetime you have many different choices to build the quantum field theory, to build the one particle Hilbert space, and therefore the Fock space, and therefore there are mathematically different notions of vacuum particle. I think still people, it's really difficult to abandon this notion of particles as something real and unambiguous. In my opinion, the Unruh effect is one of the cleanest examples that that help oneself to accept that that the particle interpretation of the field theory is just a convention-dependent statement. So here the Unruh effect refers to the fact that that observer, which is in Minkowski spacetime, so the Unruh effect happens in Minkowski spacetime, so not even in a quarter spacetime, but happens when you consider observers which are not inertial. So the statement is that if you consider an observer which is accelerating in Minkowski spacetime with uniform acceleration, so we only need to consider that simple case of uniform acceleration. That guy, if the state of the field is in the Minkowski vacuum, he will see that the state full of particles. So Minkowski vacuum, a guy which is accelerating uniformly, he will see a bath of particles around him. Even more, he will see that the state is not only full of particles, but the particles are distributed like in a black body spectrum thermally. So the state will be a mixed state and characterized by a temperature which will be proportional to the acceleration of the observer. And so what I want to do in this chapter is to describe mathematically and physically how this effect arises. So I want to start section 2, which is just classical things, just reminding you what is the trajectory of an accelerated observer in Minkowski spacetime, and define what we call Riller wedges, the right and left Riller wedges. In section 3, we will just apply all the machinery that we discussed in the chapter 4 to relate two different quantizations in Minkowski spacetime. One, the Fock space and the Fock representation defined by standard Minkowski inertial observer, the one that we described in section 2, in chapter 2, and 2, the Fock representation naturally associated to the accelerated observer. And we will see that they are different, and the Minkowski vacuum, when written in the Fock space of these guys, is a thermal state. And in the last section, this will be quite similar to the formalism of chapter 4. And in the last section, I will describe for you what I believe is a quite illuminating piece of information to understand this effect, and is what a real particle detector, which is accelerating uniformly in Minkowski spacetime, will feel about the Minkowski vacuum. So we will apply what we did in the last section of chapter 4. I just tell you that this part was due to Fulling, 1973, and Davis, 1975. So these two guys already realized that the quantum field theory that an accelerated guy will build is different from the Minkowski standard one, and they even derived the result had to do with some thermal effect, and was Unruh who interpreted all this math using particle detectors and provided some nice physics on the top of that. So in my opinion, this effect should be called Fully Davis Unruh effect, not only Unruh effect. Regarding references, there are many good references to read this. You know, I think any book of quantum field theory in corporate spacetime has a chapter called the Unruh effect. So this presentation, my presentation, is not particularly different from other ones. So you can check the bibliography. There is a nice review in addition to the books. And the nice review is Archive 07573. Also in Wall's book, there is a nice summary. In Bill and Davis' book, so there are many available references, in addition to the nice original papers of course. So just let's go over that and start describing section 2. I don't copy the title again. So let me start from scratch, just in case some of you haven't seen this before. And you know, the first assignment is that it is quite easy to show that in Minkowski space-time, the trajectory of the wall line of a point particle with constant acceleration A is a hyperbola. If you haven't seen that before, I mean, it's quite easy, I'm sure you have seen, but in case, go to Misner, Thorne, and Wheeler book, page 166. There is a short derivation of that method. We can choose coordinates. So we can choose inertial coordinates, always t, x, y, and z. So the hyperbola lies in the t-x plane, and takes the following form. So we can parameterize the hyperbola using tau. Tau is the proper time along the hyperbola. So proper time along the hyperbola. And there is always an inertial observer for which the hyperbola lies in the t-x plane and has zero velocity in the y and z axis. So this is the wall line of a uniformly accelerated trajectory. So I only need the plane tx. These are, and this hyperbola is this. Okay. Give a number 1 to this equation. So if we are this inertial observer, this guy starts from infinity, if I am this inertial observer, this guy starts at infinity with a velocity close to the speed of light, because these lines are 45 degrees, so in our units, this line is the speed of light. Acceleration is on this direction for this guy, so this guy is extremely fast there. It decelerates. At this point, is at rest with respect to me, and then accelerates back over there, and again it goes to the speed of light after an infinite amount of time. So it comes, stops, and comes back. So this is what this hyperbola is telling to us. Also, before I forget, in our dimensions, acceleration has the dimensions of length. Sorry, one over length. I don't know why I got less clear. So from 1 you can check by yourself many things. You can check that x squared minus t squared is equal to a squared. This is why we say that is an hyperbola. You can compute the force velocity of the particle, u mu. Force velocity has components dt, d tau, dx, d tau, dy, d tau, dz, d tau. And just doing the computation, you will get hyperbolic cos, hyperbolic sine, 0 and 0. So this is the force velocity for this inertial, as measured by this inertial observer. The force velocity, of course, always, by definition, has norm equal to -1. And you can, it's obvious, minus cos square plus sine square is -1. So this is okay. You can also compute the acceleration if you want. The force acceleration, by definition, is just the derivative of the force velocity with respect to proper time, and just taking derivative a cos a tau 0, 0. You can check yourself that the acceleration is orthogonal to the velocity. That is always the case. The acceleration vector is always orthogonal to the force velocity, and it's a spatial vector. And you can check yourself that the norm of the acceleration, which in GR has the interpretation of the acceleration, the square of the three acceleration standard. So this is just a standard thing. Probably all of you have seen that, but just to be sure that we all have the right equations in mind. So now what I want to do is the following. Now consider that the wall line 1, that trajectory, corresponds to a local observer. So you are an observer, you are following this line, you can make measurements in your lab locally with your rows and your clock. So that is just your local observer. This is what we call a Rindler observer. This is a local observer, but it's not difficult for us to build a global system of coordinates. You know that in GR, a global system of coordinates is given by a congruence of lines which never intersect, and they cover all the regions that we want. So we can take the congruence of Rindler observers so all these guys here, all these lines, one at each point of the space. They have different acceleration, so all they will cover acceleration larger than or equal than 0 to infinity. They define a system of coordinates in inconsistent lines. The question?
I mean, is that minus infinity or what?
No, this is the absolute value of the acceleration. From this wall line, just the weight corresponds to infinite acceleration.
So, like, I mean, is that greater than sin or less than sin?
Thank you. So all these guys define this system of reference with coordinates tau, rho, y, and z, and the coordinates that these guys are defining are related with the inertial coordinates in this way. For x. I use the same name for z and y because they are the same as the inertial lines. So this is the new coordinates that these guys define for us. And you can check that the tau coordinate labels points along the hyperbolas. Tell us in which point around a given hyperbola we are. Rho labels hyperbolas. Rho equal constant is precisely an hyperbola, and each hyperbola has different acceleration, and the acceleration of the hyperbola is given by a squared rho. So the hyperbola with acceleration a corresponds to rho 1 over a. This is what we call Euler coordinates. The inverse of this transformation, just for completeness, is t is equal rho hyperbolic sine of a tau x rho hyperbolic cosine a tau So now we have this new system of coordinates, which is different from the inertial one. The first question is what portion of the Minkowski spacetime these coordinates cover. Do they cover the whole spacetime or only a portion of it? You know, in GR, every time we change coordinates, we have to worry about what is the domain of those coordinates. So it is quite easy to note that, you know, that tau, in fact, goes to infinity whenever plus or minus t is equal to x. So tau really diverges on this basis. I'm going to make a plot here so you don't have to run every time. So what we see is that, first of all, we have all these hyperbolas. This one corresponds to some rho 1, this one to rho 2. So rho really labels different hyperbolas. Tau, as I said before, really labels. So these are lines of rho constant, these are lines of tau constant. Tau 1, tau 2, so tau labels points along hyperbolas, rho labels hyperbolas. This line corresponds to tau going to plus infinity, and this line corresponds to tau going to minus infinity. So tau diverges there. So let me just be more correct. Bars. This line is tau equals 0. also it's not difficult to see from the definition of rho that rho is real only if the absolute value of x is larger or equal than the absolute value of t, because rho is root square of x squared minus t squared. So this line also corresponds to rho equals 0. This line also corresponds to rho equals 0. And rho infinity, rho is growing on this direction, on hyperbola in this direction, and the asymptotic hyperbola with 0 acceleration is rho to infinity. Therefore, you know, our new system of coordinates is ill-defined on these boundaries. So this shadow region is the region in which we can trust this system of coordinates. So this is the patch that covers this system of coordinates. So this is what is called the Rindler wedge. And it's in fact the right Rindler wedge, because there is another one on this side that we call the left Rindler.
And that's the region which is well-defined or ill-defined?
This is well defined. The system of coordinates gets ill-defined on these boundaries. You can see here that the line tau constant and rho constant agree, so that is not a good system of reference anymore on this side. But inside the Rindler wedge, everything is fine. So just one more thing. It is many times convenient to replace the coordinate rho by a new coordinate zeta. Then the symbol is unfortunate because I don't know how to do it. So I'll try my best. This zeta is defined, or chi, or psi, or whatever it's called, is defined in this way. So that means that in particular the hyperbola, the reference hyperbola that we are using at the beginning, the hyperbola with acceleration. Sorry?
Zeta or C?
One of the two.
Okay.
I don't know how to write any of the two,
They're all
so doesn't matter. The hyperbola with acceleration a, remember, corresponds to rho equal 1 over a. Here corresponds to is. So psi equals 0 corresponds to a hyperbola which is over here and has acceleration a. Okay, we have our system of coordinates and we know what is the region it covers. Now we will work all the time with tau, psi, y and z. And the next thing I want to do is to write the metric, the Minkowski metric on this coordinate. So just go to Minkowski metric. You can check this yourself. The Minkowski metric in these coordinates is, let me write it in both, with rho and with psi. With rho is simple. And if you use psi, this is the Minkowski metric that we get. This call Riller metric. Don't get confused. It's just Minkowski metric, but in Riller coordinates. So it has zero curvature. It's just flat metric, but in those coordinates.
So we have Z and rho both in the last term.
Oh, thank you. So let me make a few comments about this metric. This construction in general. So first of all, you can see it in this line or in this line where rho is equal to 0. So this metric is diagonal. When rho is equal to 0, the determinant is 0, and the metric is not invertible, and that is a singularity. Or here, when rho equals 0 corresponds to psi minus infinity. Maybe I could say it better. Let me just add it here. This corresponds to psi minus infinity. This corresponds to psi minus infinity. And psi infinity. So, Riller metric contains a singularity. Every time we are in GR and we find a singularity in the metric, we have to wonder if that is a physical or a coordinate singularity. What do you think it is? Coordinate, because we are in Minkowski spacetime, so that nothing happens there. Our system of coordinates breaks there. So contains a coordinate singularity. In fact, it's quite similar to the Schwarzschild singularity in the event horizon. There is a very close analogy. At the limiting hyperbolas psi minus infinity or rho 0. They mean the limiting hyperbolas are called the future and past Riller horizons. Can you guess why they are called horizons?
Because you can't observe anything past them.
Because we have the two. This is what people call the future horizon. This is the past Riller horizon. The future horizon is the boundary of the events that can causally affect the Riller wedge. Any event here, if you emit light, is going to go in this direction. In this direction, can never affect what happens inside the Riller wedge. On the other hand, the past horizon is the limit of the region that can be affected by the Riller wedge. Anything that happens here will go in this direction and this direction. So this region can never causally affect what is beyond this horizon. So this is like the event horizon of a black hole. This is like the event horizon of a white hole. Of course, they are not event horizons because we are in Minkowski spacetime, so they are observer-dependent boundaries. But for that boundary, these surfaces, these hypersurfaces, has some kind of meaning of horizon. Second, the Riller metric is, so if you look at this metric, which is the first adjective that you will throw in, what is the first property that you will say from it?
Diagonal.
Diagonal more than that. That's true. Another one. It's flat, but even though it's not so obvious. More. Coefficients.
Yeah, that's.
Coefficients do not depend on time. It's a static metric. So there is a Killing vector field. So it's static. It's stationary, but it's also static. So it, and you know that that is important for our purposes, because as we saw in previous chapter, when we have a spacetime which is static, the quantum field theory has a preferred representation or a preferred notion of particles given by the positive frequency notion coming from the Killing time. So that will be important for us. So it possesses a Killing vector field. Really, it has a one parameter family. Killing, sorry, time-like Killing vector field. It is just given by the vector field that produces translations along the time, the coordinate tau. And if you want to write it in terms of the Minkowski coordinates, you can, using the change of coordinates, this is just this vector field. So you can tell yourself that this metric is lead tracked by this vector field. So this is a Killing vector field. And if you see this is just the generator of boosts in Minkowski spacetime, if you are interested. Okay, so we have that Riddler wedge, the right one, which when expressed in terms of Riddler coordinates, it looks like a static spacetime itself. Third comment I want to make, just what I said before. One can analogously define the left Riddler wedge. So you just need to do the same on the other side. You know, you have hyperbolas, etc., and everything is the same except that the Riddler left, so the left Riddler coordinates there. Riddler coordinates there are just the tau. I now add an L to mean that this is the Riddler time in the left one, has a minus of difference with respect to the right one. And the minus has to do with the fact that, you know, that this boost generator is time-like but past-oriented in the other way. But I am not going into those details. And the psi coordinate there is just root square x squared minus t squared. So I think it's the same. And the z and y coordinates are also the same. So the main difference is that we have a minus there. We have a minus because otherwise, you know, you can check that if you don't have this minus, tau decreases when t increases. So if we don't have a minus, this guy goes to the past when this guy goes to the future. So it's not an appropriate time. So we need that minus. One last comment. is that left and right Riddler wedges are causally disconnected, in the sense that any point from here to any point from here can only be joined by curves which are somewhere spatial. So their points can only be connected by somewhere spatial curves. That is true. However, I want to emphasize that the two wedges complement each other. In the following sense. If you take a Cauchy hypersurface on the right wedge, for instance, this Cauchy hypersurface here, I don't need it so sigma r, and you consider another Cauchy hypersurface in the left one, for instance, this one, and you take the union of them, that is a Cauchy hypersurface of the entire Minkowski spacetime.
Do they have to meet at the origin of the coordinate system?
The point is that if this Cauchy in order to be a Cauchy hypersurface, has to reach here, because if it only reaches here, it's not a Cauchy hypersurface.
So I'm confused about why this is able to cover all events in the space-time. Doesn't it omit some of the past history of some of the events?
No, because if you give me initial data for any field on this and this one, so this is really a Cauchy hypersurface in the whole Minkowski spacetime, to cover to the past and to the future, everything. If you only consider this one, obviously not, because if you take the past of this point, the past of this point is given by this line. So that part leaves all the points here out. But if you consider both fully cover the Minkowski spacetime.
Okay, so this counts on the fact that that the quantum field theory only depends on initial state and doesn't depend on past history in some sense.
I mean, the past history can be determined from conditions there. If you give me initial conditions today in the whole universe, you can determine uniquely the past and the future. So we call them initial conditions that that you can extend them to the past and to the future.
Okay, yeah.
So the Ringler metric is really only covering our space-like separated points, or the left wedge and the right wedge don't cover the top and bottom,
Exactly.
so to speak.
Right. So we only have a metric coordinate here or coordinate here. You can also extend the coordinates to this upper, but we don't need that, because with these two wedges we are realizing that they already complement each other. So we have initial data, Cauchy surfaces for the whole Minkowski spacetime, just considering these two. So in particular, a solution to the Klein-Gordon equation is uniquely determined to the past and future by initial data at the intersection between two Cauchy hyperspaces brought from the left-hand side. And that will be quite important in the next section. Essentially because we will be able to build a quantum field theory on the right wedge, we will be able to build a quantum field theory on the left wedge, and these properties tell us that the two together is a quantum field theory for the whole Minkowski spacetime. So we can really write the Minkowski vacuum in the union of the two quantum field theories. So that will be quite important. So this brief introduction is what I wanted to say about the geometry and these Wheeler coordinates, etc. You have any questions?
You're saying that the space in between the inside the bonds, how will you cover that? How will you use it?
If you give me initial data here and here, any point here, it's past light cone is there, so you are covering fully the past light cone. The future of this surface and the past covers the full Minkowski spacetime. That is the statement. If you give the initial condition there, you are fine. That, in other words, that is a Cauchy hypersurface. Okay. Okay. So now let's go to the third section. Coefficients and ternality. So now you already know what I'm going to do, what I explained in the introduction. The goal here is to build the two quantum field theories and compare them. So let me start doing it step by step. So first of all, we have 4 comments here, 1, 2, 3, and 4. Just emphasize that comment 2, this comment here, tell us that Riller, right, and also the left one, wedge, can be considered on its own. I don't know if it is on or in there. As a globally hyperbolic static spacetime. In other words, now I can close my eyes, take Riller metric in the right wedge, Riller coordinates, and focus on the right wedge, forget about the rest of the spacetime, and believe that that is my spacetime by itself. That the spacetime is globally hyperbolic. You can check that is globally hyperbolic. It has a metric which is static, has a Killing vector field. So forget about Minkowski spacetime. Focus on that. For you, it's a perfectly valid spacetime. But now, if I give to you a globally hyperbolic static spacetime, you know how to build a Fock quantization. And in fact, you know that there is a preferred Fock quantization, the one constructed using the Killing time as your decomposition of positive and negative frequencies. Therefore, we can build a Fock quantum representation for a Klein-Gordon field using section, what we learned in section, I think was 4.5. So in that section, remember, the title was quantum field theory in a static spacetime, so we just have to apply what we learned there here. So this is just an application of that. So we know that in that case, there is a preferred notion of vacuum, there is a preferred notion of quanta, and therefore there is a preferred quantum representation. So call vacuum with an R, the vacuum, selected by the Killing vector field partial tau. Okay. And the one particle Hilbert space HR and the focus space FR. The one particle Hilbert and focus spaces. Where R refers to the right Riller wedge. We can repeat the exercise in the left Riller wedge. So a similar construction can be done in the left Riller wedge. So we will have a vacuum there, and a Hilbert space there, and a focus space there. So, in particular, if you are an accelerated observer, this will be the quantum field theory that you will construct if you are in the right way, and this one if you are in the left way. And you don't talk, they don't talk to each other. Your universe is the wedge, and you don't know anything about what is outside. Furthermore, so now I can take advantage of comment 4. So, comment 4 implies that, that if I put the two field theories together, that will be a good representation for the whole Minkowski spacetime. And that is a key feature in this construction. Implies that the focus space built from, so take the one particle Hilbert space for right wedge, the one for left wedge, take direct sum, so mix them, put them together, build the focus space. That focus space provides a Fock representation for the whole Minkowski spacetime, for the entire just, as you can see here, that this representation is based on the notion of positive and negative frequency with respect to Riller times. Tau in the left hand side and tau L in the right hand side. So this is quite interesting. So, in this straightforward way, we have been able to build a different Fock representation for a field in Minkowski spacetime. This representation is based on the notion of vacuum and in general of positive and negative frequency with respect to times defined by a uniformly accelerated observer. Of course, this representation is different from the one introduced in chapter 2. Remember that the one was based on positive and negative decomposition, positive and negative frequency decomposition with respect to the time translation inertial times. Inertial times with respect to the inertial times, any of them t. So the two notion of times are very different from each other. So the two Fock representations will be different. So our goal here is to let me call the Minkowski vacuum to that vacuum as we did with an M, the Minkowski one part of a Hilbert space with an M, and the Minkowski Fock space built in chapter 2 using inertial times with an M. So our goal is to formally write Minkowski vacuum in the Fock space defined by Friedler observers. So this is our mathematical goal, well-defined problem. And then I can do that because this is a good Fock space for the whole space-time. But so this step is mathematically well-defined, except for some subtlety that we'll mention later on. But remember that our question is how the Minkowski vacuum is seen or is being observed by one of the accelerated guys. For instance, the one living on the right wedge. So what I want to do is after this, then project on one of them. So take the Minkowski vacuum, project, so write it in the two wedges, and then project over one, and that's because the right guy has no information about the left one. So for a guy living on the right, the information on the left is inaccessible. So what you have to do to really compute the Unruh effect is to write this state here, and then project over the information or trace out the information on this way. So this is what people call part of the Unruh effect. Do you have any guess what is going to be? I mean, you know what is going to be the result because I told you before. I told you that the result is going to be a mixed thermal state. Do you have a clue why a mixed state? The Minkowski vacuum is a pure state.
Like whole is pure, but since we are going for part like subsystems, so it will be mixed further.
We are tracing out the information here. So all the correlations which are between these two H's will be. I will go over that. I'm just advertising the result. So essentially, we will discuss that. So, and do you guess what do I have to do to do this? So the first step, what could you do to write the Minkowski vacuum on this Fock space?
Actually, writing in paper.
Sorry?
coefficients.
Compute the Bogoliubov coefficients. So compute the modes that are expanding these Fock spaces, so the positive frequency modes with respect to the Riller time, and take the Minkowski modes that we know what are there, and compute alpha and beta. And with that, and using the expressions that we had in chapter 4, we can write this state in this Fock space. I mean, we already did it. We only need the expressions for alpha and beta. So this is what we have to do. So we need to compute Bogoliubov coefficients. So and this is the computation that I start right now. Again, to compute alpha and beta, what we need is to know the two set of modes. We know the Minkowski modes. We need to know first the positive frequency modes with respect to tau and tau L. This is what I'm going to call Riller modes. So now I'm going to start that derivation. I'm not going to give you every single detail because it will take too long, but I will give you most of the information, so any of you should be able to complete the missing steps. So, what do we have to do? The first that I would do, remember that the modes that we use to decompose the field are solutions to the wave equation, which has positive frequency with respect to the times that we want to work with. So first thing I have to do is to write the wave equation in my coordinates and find solutions of that wave equation with positive frequency with respect to tau. So let's start with the right weight. Both are similar, so just I will do the right and I will tell you what you have to do to obtain the left ones, which is just changing a couple of signs. So let's begin with the right weight. So first of all, the Klein-Gordon equation. The Klein-Gordon equation, is this one. Is this the most general form of the Klein-Gordon equation? Question mark.
Is this,
Yeah.
What about if I add a term R?
Oh, yeah, we can.
But R is 0 here, we are in Minkowski. So yes, this is the most generic one because R is equal 0 in Minkowski spacetime. So I don't need to consider non-minimal coupling because all of them are exactly the same. So this Klein-Gordon equation in right Riller coordinates. So if you are an accelerating observer and you want to solve the Klein-Gordon equation, you use your coordinates, and this is what you are going to obtain. Partial tau square plus partial minus partial y square minus partial z. This phi tau psi y and z equal to 0. And you can check this yourself, which is one line computation. So this is the Klein-Gordon equation. It's quite simple. It's almost the Minkowski spacetime one. Maybe I am missing a minus here. I am not completely sure that it is very likely that I am missing a minus here. I will tell you next time. So this is a quite simple equation. The only thing is a partial differential equation with coefficients that only depend on psi. So no time dependence, no x dependence, no z dependence. Sorry, no, there is no x. No y, no z dependence.
Where did mu square go?
Sorry?
Where did mu go?
I think I You will tell me when you do the exercise. I don't remember off the top of my head. So it may be a minus. So we have to solve that equation, and in particular we are interested in the solutions with positive frequency with respect to tau. So do you guess? Can you tell me what are those solutions, or how would you, or part of them? And it's quite simple because nothing depends on tau, so e to the temporal part can be e to the minus I omega tau. That will be good temporal part. Nothing depends on y and z, so the y and z part can also be e to the I k y y plus k z z. The non-trivial part is only on the psi variable. So this equation admits solutions of the form, and this is what we are looking for. Let me call the modes as usual, bar phi with an R because we are in the Ringler wedge. The modes now will depend, as in Minkowski, will depend on 3 levels. So these are the 3 levels that level our nodes. Remember, in Minkowski spacetime, the modes are leveled by the 3 components of K and are just e to the minus omega t minus kx. And if you give me k, I know what is omega. So with 3 levels, I have enough. Here, also with 3 levels, you have enough. But because the easy part is the time and y and z, I use the levels for time, which is omega, and this is just kx, ky, kz. So I use these 3 levels. I could also do that, use ky, kz, and omega. Here I need to do that because the non-trivial part is on the side coordinate. So these are my levels. These modes are going to depend on the 3 coordinates. And as I said, the non-trivial part, let me call it f, depending on the levels, is the part that depends on psi. The other part is trivial. It's omega tau over root square of 2 omega e to the I k tau x, where x orthogonal is just y and z. I call it orthogonal because it's orthogonal to the plane in which the acceleration happens. The acceleration happens in the z, in the x direction, so y and z are the orthogonal part. The statement is that these are positive frequency modes with respect to tau, and where these guys are solutions to this equation if the psi part satisfies the following equation. Minus e to the 2 a psi So if f satisfies that equation, these guys are solutions. Where this f only depends on psi. So as I said, the non-trivial part is only on the psi variable. But this equation is quite familiar to you. This is like a time-dependent Schrodinger equation, which is a time independent. Schrodinger equation like with potential V only depends on the xi coordinate and is exponential potential e to the 2. And you can think, sorry, times k orthogonal square minus mu square. You can think yourself why, the Klein Gordon equation, which we know what it is in Minkowski spacetime, in inertial coordinates, it's just partial second derivative time plus minus second derivative space equals 0. Here becomes an equation with a given potential. So when you go to an accelerated frame, what is a free equation with no forces appears equation with a potential. So this is kind of inertial forces. There is no force on no potential on the field. It's just a fictitious potential because you are accelerated. So this is kind of fictitious potential. And you can think why it depends on the orthogonal of the momentum of your quanta orthogonal to the direction of that acceleration. So I just encourage you to think about it.
So it will be like everything will be like simple. I mean, like transmitted wave, reflected wave, tunneling effect.
The only thing is that this guy is exponential, so there is no transmission.
Oh, yeah.
Everything will be the same.
Yeah.
So it's an exponential. So it's a potential which in this region v goes to infinity here. It goes to 0 in this region because this is chi minus infinity. This is chi infinity. So particles are free here, but you have a mode moving in this direction. It will be reflected. It propagates the speed of light. So it is not difficult to find exact solutions for this equation. So as we just pointed out, physical solutions will vanish when goes to infinity because the potential goes to infinity, and will be, it's quite curious because, this potential depends on the mass of the particle, so part of the potential is coming from the mass. But, when psi goes to minus infinity, this goes to 0, and the potential kills the mass. So in this region, the field doesn't even feel the mass. So the potential kills this term completely, including the mass. So this is quite similar to what happens in a black hole. In a black hole, if you go close to the horizon, there is a blue shift given by gravity. Gravity in the horizon is very strong, the wave is very weak. So if you have any light ray with low frequency, low energy, far from the black hole, and you propagate it close to the black hole, there is a blue shift, and it has a lot of high energy close to the black hole. So this blue shift is exponential when you go close to the black hole, and it really, gets rid of any other scale that you have in the problem. If you have a mass in the problem close to the horizon, the red shift, the blue shift is so high that you don't care about the mass. Something similar is happening here. When you go close to the horizon, this potential, which is a fictitious potential, gets rid of the mass, and the field behaves like a massless field on this picture. There are a lot of similitudes between the regular spacetime and a black hole spacetime.
But this is all like, we started with this, what is that called, removable singularity, right?
Right. In the Schwarzschild solution also, if you use Schwarzschild coordinates, you have a coordinate singularity close to the horizon. In this case, it's a fake because it's just because you are using some. There is nothing happening there. There is no really horizon of any kind. In the black hole, there is a horizon, but the maths are very similar. And in fact, the Unruh effect has been one of the guiding toy models to understand better the Hawking effect. So people have used a lot the Unruh effect as a toy model for the Hawking effect. You have to be aware what are the differences. But if you are aware of that, there are many things which are extremely similar. In fact, if you are sitting in front of a black hole at radius constant, you are accelerating with constant acceleration. You know, with absolute acceleration equal constant. So it's very similar to that. And this thermal result that we are going to derive is also very similar to the thermal Hawking radiation. Okay, so physical solutions will vanish very far from the horizons and will be left and right moving. So it will be a combination of left and right free waves of this kind e to the minus omega I omega tau plus minus psi. So the plus corresponds to left moving or right moving and the other to minus. When k goes to minus infinity, because the potential goes to 0. So we want to find solutions to this equation with these physical properties, just given by the potential, as you would do in quantum mechanics. And the statement is that there are exact normalized modes with these properties are the following. So just let me put everything together. The positive frequency modes in the right Friedler wedge are modes which depend on the 3 coordinates, on the 4 coordinates, sorry, and are given by the following expression. They are not simple, they are not complicated either. They could be more complicated. So the y and z dependence is just exponential. The time dependence is also exponential. And now the other dependence, which is a solution of this equation with these properties, is the following. Hyperbolic sine 1/2 of now one of these modified Bessel functions with that index. This is the index of the modified Bessel function. And in the argument we have k orthogonal square plus mu square I think I am writing a sign incorrectly. I think there is a plus here. Plus here. So these are the positive frequency modes. So positive frequency, right Riddler modes. Just tells you that this k mu of x is a modified Bessel function. That you can find in any book. Just let me say 2 more things about this. We are in a very good shape. We have the modes. We can compute alpha and beta just taking Klein-Gordon product with the positive and negative Minkowski frequency modes. So that's it. So warning, as in Minkowski spacetime, these modes, because omega is continuous, they are normalized to the delta function here, the Dirac delta of 0, as happened in Minkowski spacetime. But we know what is that. That is because physically what you have to do is to consider wave packets which are highly peak on a given omega, but not exact given omega. Then they are normalized to the Kronecker delta and everything is fine. So solution could be work with wave packets. As we discussed in cosmic spacetime. But you know, wave packets are very messy computationally, so as long as you are aware where these divergences come from, you can work with plane waves with this continuous normalization, and everything is fine. But just keep that in mind. Two more things, and I finish. So as you can imagine, these guys, the set of all positive frequency Riller modes for all omega and all k are a basis of the space of positive solutions in the right Riller range. So from here we can construct, this is the basis that we use to construct the one particle Hilbert space and the right Fock space. Okay? So this is nothing new. Now, by replacing tau by tau L and psi by psi L, we obtain the positive frequency modes on the left Riller range. So positive frequency modes in the left Riller wedge, and they form a basis of S plus in the left Riller wedge. And the last piece of information I want to give to you today is that, you know, although the right and left nodes have been defined in the right and left wedges, respectively, it is very easy. They can be extended to the full Minkowski spacetime by analytical continuation. Which is I don't write the details, but it's just straightforward.
Ivan?
Yes.
Ivan? And this analytical continuation is essential to see Unruh effect.
It's essential, right? Because you know you need to write the Minkowski. Sorry, you need to write the Minkowski modes, the Minkowski positive frequency modes, as a Bogoliubov transformation of the left and right Riller modes. So you need these left and right Riller modes to be defined everywhere. Otherwise, you cannot rigorously write the Bogoliubov transformation.
Yeah, thanks.
Thank you
Thanks.
for the comment. It's very important for that because I mean, you know, in the next section when you derive the Unruh effect using particle detectors, you don't need all that. because you just has a particle detector which only lives on the accelerated trajectory. So you don't need all this machinery. You don't need to extend modes out of the Riller wedge. So you need that on this more mathematical derivation. So I want to stop here, and we are in a good shape because we have all the ingredients that we know that we need. So we have a quantum field representation on the right wedge, another on the left wedge given by Riller observers, and now we are ready to write the Minkowski modes as a Bogoliubov transformation of the right and left modes. So we will have, symbolically, we will have two kinds of alpha and two kinds of beta. One alpha, or if you want, symbolically, we will find Bogoliubov transformations of this kind. So we have a basis of modes in the whole Minkowski spacetime given by these four guys, positive and negative frequency modes, and we can write the Minkowski modes as a linear combination of them, and the coefficients are the Bogoliubov coefficients. So we already have these four guys, so next day I will tell you what alpha and beta are, and we will write directly the Minkowski vacuum on the direct product of these two Fock spaces. And today is over one, and see what the state is. And it gives you quite a good idea of how non-trivial is the Minkowski vacuum. But, one thing that the vacuum is the less interesting state, and that is not true. We will see that the vacuum is full of correlations, which when you restrict the vacuum to a way, it's full of particles, the thermal state, so showing the richness of information that we have in a vacuum, and even more, showing directly that this notion of particle is just convention-dependent statement. So I want to stop here. If you have questions, go ahead. If not, we continue on.
If this happens in the Minkowski space quantum field as well, the Unruh effect.
This is Minkowski space.
No, so the Unruh effect, does that happen in the flat space quantum field theory?
But this is the flat space quantum theory, isn't it?
Yeah.
So this is just.
So it's not a feature of only the curves.
No. I mean, I am working all the time in Minkowski spacetime. So this is Minkowski spacetime. The only thing is that I am considering accelerated observers. So this is the new
I'm
feature.
asking, why is it a surprise for someone who has worked in, say, in particle physics?
Because you have this idea, intuitive idea that a particle is a ball, that it goes there with some momentum, energy, charge, and spin, and the particle is there. You measure it or not, but that's not true. I will show to you that if you have the Minkowski vacuum, so you are sitting here with your detector, you measure this complete vacuum, absence of particles. But now Caddy starts running very fast in an accelerated way with a detector in his hands, and he will start detecting particles. So he will say, no, this is not the vacuum at all. This is full of particles. Who is right? Both are right.
That can be tested experimentally, right?
Yes. The only thing is that we will show, you need very high accelerations to produce that, to produce some observable effect. But that can be in visible testing. So if you are accelerating in the Minkowski vacuum, that state is not vacuum for you at all. Your detector, particle detector in your hands. This is why this next section I think is quite illuminating, because this is a bit mathematical and people. You have a detector in your hands, particle detector. It will beep all the time. You will see particles around you with a spectrum given by a thermal distribution at some temperature given by your acceleration.
Did you say it has been tested, or in principle
No,
it hasn't?
In principle, could be. The only problem is that, as we will see, when you put numbers, you need huge acceleration to produce that.
Like, just very, very big. Like how big, perhaps?
Back to the 20
That's
meters
quite big.
second
Okay.
square. So.
Can you not do that in the gravitational field of some big
A black hole, which is quite similar to study Hawking radiation, that you need very small black holes to produce a temperature which is large enough.
those if you do.
But something quite similar is what happens in the early universe, that you have expansion, you have something similar, particles are created, that we see them in the CMB, so if you want, that is an observation of all these effects. But if in this Unruh effect, in inclusive spacetime, no curvature, just considering accelerated observers, really tells you that the notion of particle is completely observer dependent. In that case, you could say, no, but there is a right one. The inertial notion of particle is preferred. Okay, but the example shows to you very obviously that in another context, when you don't have a killing time, the notion of particle is completely observer dependent. The particle interpretation of a proof theory is just an interpretation which is a basis dependent.
How do we know that this is not simply just an artifact of our theory, but kind of like a phenomenon that we can observe? There seems to be I feel like I want to make a distinction between, I don't know if the fact that this is convention dependent is, do you kind of get what I'm kind of feeling here?
I mean, this is why in particular, this is the reason why I went with some detail on these particle detectors, because the other derivation, this derivation can sound mathematical for many people.
Yeah.
You say, okay, you have two bases, you decompose it, this is the way you define particles mathematically, whatever is created by the creation operator, but how do I relate that with nature? How, this is why the particle detector example I think is very illuminating, because that is just take a particle detector and see what you detect, and this is what you call particles. Mm-hmm. When the particle hit your face, it's because you have detected it with your face. And so that is telling to you that physically you will see particles.
Okay.
So this is the mathematical derivation. In next section I will do the same in this particle detector, and you will see that the results are compatible with each other. So if you are more mathematically oriented, this is for you. If you are more physically oriented, the particle detector is for you.
Not just the existence of the cosmic microwave background, but our acceleration relative to the rest of the universe. Is that sufficient?
No. That's bigger acceleration.
Okay.
But they don't work right. There are many papers in that you see people who have tried doing huge acceleration. Sorry?
I think there is some people, experimental people working in condensed matter, that they already has confirmed some kind of measurement about.
There are, but they are more close to black hole geometries than to the Unruh effect.
Oh yeah, of course. But
so
it is a closely related
right,
phenomenon, so probably.
Right. So we will mention that on the chapter of Hawking effect, that you can simulate the physics of Hawking effect with fluids, and people have claimed to be detecting this, but there is no consensus on that because people.
Unruh himself.
Right, but if you see what he says,
to measure, but I think he is not.
He cannot see directly the Hawking radiation from the black hole because it's too small, it's well beyond the thermal noise of the fluid. So he has to use a stimulated emission, which is the stimulated counterpart of Hawking radiation, but that is purely classical, so it is nothing. It's not. He claims that signals the Hawking effect. That some people say that is a purely classical effect,
right?
And it's subtle. But people is working hard on that in these analog systems using fluids. So. But for me, the CMB probably is the most clear observation on this kind of effects. So we will go also over that in a couple of chapters.